Here are the topics that we'll discuss today. First, we'll discuss about strain energy and strain energy density. And then we'll discuss about strain energy density for general stress state, more complex situation. And then we'll discuss about impact loading problem, which is this problem. So let me begin from the first topic, strain and strain energy density. So before begin, let me give you a short review on general physics problem. So back in general physics problem, we sometimes got asked this question: what will be the maximum displacement of a spring hit by a ball moving with velocity v? So we can solve this problem using Newton's law, like using acceleration and force and etc. Of course, out of this method, by integrating the acceleration to obtain the velocity trajectory, and from velocity, by integrating it, we can obtain the x, and we can obtain the answer for this question. However, it takes a long time. However, instead, if we use the energy conservation method, the kinetic energy converted to the potential energy 100% at maximum displacement, and based on this method we can approach the problem in much easier way. So the advantage of this energy method is that it gives much easier way to obtain solution in some classes of problems. Okay, so we're gonna do the same thing. So let's first define the strain energy. Strain energy is similar to what you already have here, the potential energy. So if you try to extend, for example, this actual bar with force P, and if you draw force and displacement relationship, you're gonna have this triangular shape, and the area below will indicate the energy accumulated in this beam as a form of strain energy. Okay, and this energy accompanied with the strain change of the structure, we call that as strain energy. And how can we define the strain energy density? It is also useful quantity to define. So strain energy density is a strain energy stored per unit volume. Okay, so for this specific problem, because the stress distribution is uniform over the entire structure, our strain energy density will be uniform. However, for general cases, actually strain energy density is a scalar field that depends on the position of the structure. However, for simplicity, let's consider strain energy for this problem. To obtain strain energy, this is the strain energy, and you have to divide the volume, which is the cross-sectional area multiplied by the length of the beam. And if you divide this, and let's move this L, at the denominator of P, and move this L to denominator of dx, what you're gonna find is that this is infinitesimal change of strain. This is the stress definition. So what you can see here is strain energy density is integral of sigma x d epsilon x. Now, if you use the material relationship, the Young's modulus definition, epsilon x is sigma x over E. So you can either you can plug in the place of sigma x. If you plug in E times epsilon x, that will give you the value of strain energy density, and it becomes either half E epsilon square or sigma x square over 2E. Okay, so whatever definition you use, they result in same answer. And we only discussed about like x component here, but you can have y component and z component of epsilon, and gamma xy, gamma yz, and gamma zx component, and associated strain energy. Okay, so this is the definition of strain energy density. Now let's try to obtain strain energy for the problems we considered in chapter 1 through chapter 8. So let's consider the like a normal stress case. So under the normal stress, for example, suppose that we only have x component of normal stress. Our total strain strain energy can be written as integral of strain energy density multiplied by infinitesimal volume integration over the entire volume. So this u can be written as sigma x square over 2e, or half e epsilon x square. Okay, whatever expression you want. Yeah, you just use whatever you want. So let's first consider axial loading, which gives us this relationship, normal stress out of a force. So sigma x can be written as n over a for this problem. So if you plug in n over a in the place of sigma x, you're gonna end up having this relationship. And fortunately, this n over a is constant for most case. Even though it's not constant, even though we consider this continuously varying cross-sectional area, we can still use this relationship because the dv can be written as a times dx. So if you plug in a times dx, then you can be strain energy of the beam under axial loading can be written as integral over 0 to L dx n square over 2EA. Now let's consider pure bending, another case where we have normal stress. This is the case where the moment generates normal stress. So our job is same. So starting from the definition of strain energy, we plug in our flexure formula sigma x in terms of y, which can be written as minus my over I. So if you plug in this expression here, and it can be written as m square y square I square here. Now if you also plug in dv equals to be dA dx, you have to separate dA dx in this way, because you can see that previous problem at given x, the n was constant here. However, in this problem, given x, the y is different at different positions. Like this is y maximum, this is y equals 0, this is y is minimum. So when you convert to this, you have to be careful about putting dv equals to be dA dx. However, when you look at this equation in a closer look, what you're gonna find is that after plugging in dA dx, you found that y square dA integral. So if you found that if you perform the integral over dA and then dx later, so please do not confuse. Originally you have this integral instead of this integral over the entire volume. You do integration over the area first, and then you integrate over the length. Okay, so if you do integration over dA first, it becomes resulted in the definition of I. Then you can get rid of I and I here. So you end up having u equals to be integral from 0 to L m squared over 2EI dx. Okay, so that's the case for pure bending. Now let's move on to the shear stress case. Similar logic, shear stress under the pure shear stress, you can have the strain energy density can be written as half tau gamma or tau square over 2g. If you plug in this expression here, you end up having u equals to be integral tau square over 2g dv. Now let's first consider pure torsional loading. So in this case, the tau shear stress can be written as a function of radial position rho, t rho over j. J is polar moment of inertia and t is applied torque or torsion. So if you plug in this in the place of tau, then u turns out to be t square rho square over 2gj square. Now what you can see here is dv can be split into dA and dx, and you perform integral over dA first and integral over x later, and what you're gonna see that it can be identified as the definition of j, and after the rid of j, you end up having strain energy for torsional loading is given as integral from 0 to L and t square over 2gj and dx. That's the strain energy for the beam under torsional loading. Now let's move on to the final case, shear force V. So until now, here we discussed about this case, and finally we have to discuss about shear force generated shear stress case. Here the complexity arises that in addition to shear stress, we have normal stress. Actually, when you have both normal stress and shear stress, what you do is you can simply sum up strain energy from normal stress, strain energy from shear stress, and that will give you the solution. So let's solve the problem. So for general cases, it's not easy to obtain the solution for shear force case. So we'll consider relatively simple case. We have rigid wall, we have cantilever beam with a point force P acting on the right end of the beam, and the dimension is given as usual. The length is L, thickness is B, and height is H, and the X is starting from origin at the left hand. So I is given as 1/12 AH square, V is given as P, then you can also obtain m as a function of x as minus L minus xp. Okay, so m is 0 at the right end, but m becomes maximum at the left hand. Now we have two components, the strain energy from normal stress, strain energy from shear stress. So strain energy from normal stress, we have the expression m square over 2ei, and we have expression for m is given as minus L minus xp. So if you plug in the expression here, and it becomes L minus x square and p square and divided by 2ei. After performing this integral, L minus x square dx integral from 0 to L, we're going to end up having p square L cube divided by 6ei. That's the strain energy from normal stress. Now let's try to obtain the strain energy from shear stress. Here you need the expression for shear stress, and we obtained the analytic expression for shear stress in many weeks ago. So if you plug in the expression, it becomes 3p over b 2bh, and it becomes multiplied by 1 minus y square over c square. C is the largest distance from the centroid to the top or bottom of the beam. So after identifying this equation from some previous lectures, and also identifying that dv can be written as b dy dx, so here out of this integral zone, you take b dy multiplied by dx. Dx is the distance along the axial direction. So if you plug in this expression b dy dx, then you can consider integral over different y points. So after plugging in the expression for dv, then it's time to perform the integral in one by one. So you have to perform the integral over dy first, dy from negative c to c, and you do integral over dx from 0 to L, because the origin of Lx is here and the end point is here. About the y, this is y equals 0, and you have a minus y and c range to cover the entire cross section. So after performing this integral, you can do this integral by yourself. I will just skip how to do it. So the strain energy from shear stress turns out to be 3p square L square over 5ga. So the total strain energy from both normal stress and shear stress turns out to be this guy plus this guy, which we already obtained here and there. And you can massage this equation as the u sigma multiplied by 1 plus something. This is the additional term that, and after multiplying to here, which becomes the second term here. So the reason why I write them in this way is that typically this term inside this parenthesis is quite small. This can be correction due to tau. If this term is very small, not 0, very small, like very smaller than 1, you can say that u is around u sigma. But if this term is not very small, if it's comparable to 1, you can say that u can be quite larger than u sigma. Okay, so when this separation happens, so what you can see here is this is the dimensionless number. H is dimension of length, this is dimension of length, and G and E, it is dimension of modulus. And typically what you can realize for most material is the shear modulus is larger than E over 3, Young's modulus divided by 3. So if you plug in this relationship into this expression, what you can realize is 3E h square over 10g L square is smaller than 0.9 h over L squared. Now, when L is about 10h, which means that aspect ratio of 10, what you can see here is h over L is 0.1. This guy, the correction factor becomes 0.009, which is 0.9%. Okay, so compared to 1, if please imagine like doing 1 plus 0.009, then it becomes 1.009. So whether you add this term or not, your answer will be almost the same. So this is the case when the aspect ratio is around 10. If aspect ratio is small, if L is similar to H, then this factor becomes the correction factor will be almost 0.9, which is comparable to 1. In this case, what you can see here is the effect of shear stress on strain energy, and the deflection will be large. Okay, so here we finally got the answer about the validity of Euler-Bernoulli equation, even though we just considered one special case, which is a cantilevered beam under point force. When the aspect ratio is quite large, the contribution of shear stress is relatively small. When aspect ratio is small, when L becomes similar to H, the contribution from shear stress becomes significant, and you cannot ignore the deflection due to shear force. Okay, and it is a so-called Timoshenko beam theory, and it will be beyond the scope of this course. However, because we already obtained almost exact, quite accurate strain energy combining normal term and shear term, if we use the energy method, we can obtain the deflection of a beam also to reflect the effect of shear stress. Okay, so regarding that, we'll discuss about it in next lecture. Okay, so for today's lecture, let's just stop here, and just to please be satisfied by learning the definition of strain energy and strain energy density. Okay, so let me stop recording this video here.